everyone. We are back here at Build Stuff 2020. We have Vlad with us, and greetings, Vlad, to Israel. How are you?
I'm fine, thank you.
So, Vlad, I could name your 15 years of experience as a software engineer. I could name the conferences that you have been as a speaker. But one thing that I have read, what is that sufficient number of cats? Sorry if I missay it. Sufficient number of cats. What is the number?
Yeah, so look, me and my wife, we said we want to have 2 cats at our home. 3 is going to be way too many. We cannot handle it, and now we have 5. So that's the number, 5 cats.
Okay. Is that sufficient or still in process?
I think I called it almost reasonable number of cats. So
okay.
I think it goes to the direction of being not reasonable.
Okay, Vlad. So it's very, it's very good to have you here. I hope that you are ready. We're going to hear your presentation, testing software architecture. Are you ready?
Yeah, of course I'm ready. And first of all, thank you so much. Thank you so much for having me. It's such an honor to be speaking at Build Stuff for the second time.
Yay, thank you. So let's rock this stage. Vlad, go in.
Sure. Okay, so I guess I can skip that boring part of introducing myself and telling you about where I'm from and how many cats I have and what I'm doing. I'll just, I want to start with a short story. So about 9 years or so ago, no, 10 years ago, I was working at a company and my team inherited a project. That project had passed many, many hands. And each pair of hands made its code base even worse than it had been before. So over the time, that project became a big, stinky pile of code. It was so bad that at some point it was almost impossible just to look at it, just that side of methods and classes all spanning hundreds and even thousands lines of code just made your eyes bleed. And of course, the state of that code base didn't improve a bit after each new release. It just degraded more and more. The whole team hated this project. I hated it. And no wonder that when a friend of mine called me and offered to join him as a chief architect for a new startup company, I agreed just like that, without thinking about it. The company was called Khononov. Now, the most important thing about that company is that it doesn't exist anymore, which means I can say whatever I want. So not only the Khononov was a greenfield project where we had to build everything from scratch, but I also had the freedom to make all the architectural decisions. So to prepare for this adventure, I've got lots of books on design patterns, domain-driven design, and software architecture overall. I read all of them cover to cover, and I promised that this project is going to be designed by the book, following all the practices and principles of clean code and modular architecture. So I invested lots of time and effort looking for that perfect architecture. Architecture that would allow us to quickly implement new features, a design that would allow us to quickly introduce new engineers to the code base, and of course, that system had to support automated testing of all business logic. Now, even though things looked quite promising in the beginning, not everything went as planned. The more functionalities we added, the more architecture had to change. We had to migrate patterns, libraries, frameworks, and even change the programming languages that we were using. And honestly, each such change had a pretty negative impact on my ego. Lots of effort have been invested in that perfect architecture, but it looked like it didn't stand the test of time. Now, that's what I thought back then. But today, 8 years later, my point of view has changed a bit. Because, over these years, our business domain has been continuously changing and evolving. The company was continuously learning from its mistakes. The different business processes were optimized and improved. And sometimes not only that new profit opportunities were evaluated, but someday we even changed our whole sphere of business, our business domain. Also, during these years, our industry saw lots of technology-related changes. We've seen patterns, architectures, and whole infrastructures come in and out of trend. And of course, we could not predict all these developments. We had to make assumptions, test them out, and in some cases, change our minds. Eventually, that system was serving in production for over 7 years. During these years, the R&D team that implemented that software had changed many, many times. We even moved the engineering center from Israel to other countries. But despite all of these challenges, that code base didn't degrade into the legacy status. It always remained in a pretty good shape. And that's not because our initial architecture was perfect. No, it was like far from it. However, the constant reevaluation of our design decisions and constant evolution of the system's architecture allowed us to keep it in shape throughout all these years. And in this presentation, I want to share what we learned about the testing aspect of software architecture. I want to talk about how to test architecture, how to detect weak spots, how to do it before the system degrades into a big ball of mud, and of course, how can we automate many of such tests. But first, I want to torture you a bit with some theory. Let's talk about software architecture. Why is it so important? Why can't we just, hack something that compiles and probably works and just deploy to production and just be happy? Why do we have to think about software architecture? And actually, I want to ask a basic question. What is software architecture? And I would love to hear your opinion in the chat here. What do you think software architecture is? And I know there is this delay of 20 seconds, so I'm going to be patient. If needed, I'm going to fill the space with some dead jokes before I receive your answers. What does Master Yoda said when he saw himself on a 4K TV? HDMI. So the decisions that are hard to change later and not be able to defer to the future. Effective components interconnection. Design for volatility. Yeah, I love these answers. Actually, that's exactly what I wanted to hear. Cool, so let's go on. So when pondering this question, what is software architecture? Usually we have these two quotes that come to mind. The first one is by Ralph Johnson, who famously said that architecture is about the important stuff, whatever that is. And Martin Fowler, who said that software architecture is those decisions which are both important and hard to change. Now, both these quotes stress the importance of architectural decisions. And of course, they are important because a thought-through architecture is essential for delivery of the system's functional and non-functional requirements. Also, today, software systems are often an integral part of modern business. So software architecture is essential for the competitiveness of the company that is using that system. But as Martin Fowler says, architectural decisions are often hard to change. For example, in that startup company that I told you about before, We had to choose the infrastructure to run on. Should we run on our own servers or go to the cloud? And that question wasn't any trivial 8 years ago. What about the database? All of us had only experience with Microsoft SQL Server, but at the same time, we wanted to explore the brave new world of NoSQL databases. How should we architect the solution? Should we go with the traditional monolithic style or implement the system with SOA? SOA is what they called microservices back then. And of course, we had many arguments about languages and frameworks. And in Israel, we love arguments. Arguments about languages almost led to religious wars at our company. So all of these decisions directly impacted our ability to deliver business goals. And that made these architectural decisions not only hard, but also full of risk. One wrong decision and the complexity of the system would skyrocket. That's why I think the goal of software architecture is to manage the complexity of the system that we are building. And we manage this complexity usually by decomposing systems into sets of interconnected components, modules. These modules, they can take different forms. They can be classes, namespaces, services, or whole systems. But at whatever level they are, modules make it easier to comprehend the responsibility of each module individually and to understand how it interacts with the rest of the system. Modularity also alleviates reasoning about the system as a whole, how the system works and what the system is supposed to do, what are its goals. From the technical point of view, modules allow us to limit the scope of architectural decisions. For example, each component can use whatever database is more convenient for its own needs. And if there is sudden need to migrate from one database to another, then change will only affect the module itself and not the whole system. So actually, modularity, or using modules, divide the complexity of a system into two types. The first one is local complexity, a complexity of a single component. And the simplest heuristic, both for describing the notion of local complexity and demonstrating it is asking, let's say you have a component, well, how hard or how easy would it be to introduce a junior team member into its code base? So for example, at Internovus, we had a component which was in charge of managing sales agents' commissions. So its public interface, all those methods resembled a coherent set of actions related in one way or another to these commissions. Now, since its business scope was pretty limited, it was pretty easy to understand how that module was implemented. On the other hand, at some point of time, we had a component that was in charge of managing advertising campaigns, publishing them, managing contracts with publisher, and even managing the company's finances. For the second one, let alone junior developer, at some point of time, I had no clue what that thing was supposed to do. So clearly, the first component had a much lower local complexity. The second type of system complexity is global complexity. This one reflects the level of interconnectedness of the system's components. When the global complexity is low, it is easy to understand what role each component plays in the system, and when that component has to change, that change will have a lower impact on the rest of the system, on other components. Now, for example, in this slide, we can see a relatively simple, from global perspective, a global complexity perspective system. And I say that it has a relatively low global complexity compared to this system, because here we can see the same number of components, but they have many more connections and dependencies between them. Here, a change of one component will have a bigger impact on the rest of the system, compared, of course, to the previous one. Here, the changes are going to be more contained in the components themselves. So to sum it up, the decomposition of a system into modules or the design of modules boundaries is a key architectural decision. It allows to manage the local complexities of the components and the global complexity of the whole system. And that's why, in my opinion, Ruth Malan gave a much more clear answer to the question of what is software architecture. She says that it is inherently about boundaries. What's in, what's out, what spans, what moves between the boundaries, and what are the trade-offs we are making in the design process. Software architecture is all about defining the right boundaries. Over the last few decades, our industry tried different ways and processes of looking for those modules boundaries. In the days of waterfall, we had the big design up front. We tried to plan all the tiniest details of the system way before beginning actually working on it. And usually such efforts didn't end well. This approach resulted in rigid design that fell apart pretty quickly. When Agile came along, many used it as an excuse to do away with architecture. Instead, people were just building something that works here and now. It could even seem productive initially, but after some time, an architectural hangover came along, and suddenly the system became impossible to evolve and to maintain. Next, we tried having person in the role of software architect. And this approach has a few major flaws. First, architectural decisions can become personal. If something is wrong and has to be changed, it can take time for the architect to acknowledge that, especially if there are people who will tell him in that moment, hey, I told you so, I told you so. As a result, evolution of the system will drag on and will be executed when it's already too late. Second, when we divide the roles of designing the system and implementing that design, we are reducing the feedback. Usually architects don't eat their dog food, but feedback is essential for a healthy system. An architect needs feedback, whether that design or whether developers always have to invent some creative workarounds to implement some of the system's features. And finally, the approach of evolutionary architecture started gaining traction lately. The core idea of evolutionary architecture is that architecture should evolve incrementally on par with the system. And the goal of this approach of evolutionary architecture is not merely changing the design, but adapting it to the ever-changing business needs. As a matter of fact, a system's design will always change, whether we want it or not. However, more often than not, it will change for the wrong reasons. Software, as all systems, is subject to entropy. No matter how tidy and clean it was in the beginning, without proper maintenance, over time, it will decline into chaos. In other words, I guess we all had encountered really messy code bases. But I think we can agree that none of those messy code bases started with a team of engineers like standing next to a whiteboard and thinking, hey, what is the worst possible way to design a system? I want to believe that's not the case. I believe that we all want to be proud of our work and do the best job possible. However, the hardest part of architectural design is not greenfield projects, but the moment they become brownfield, when the project is already in production and its requirements are changing and we have to introduce new features. And if we are not properly managing the complexity of the system at this stage, it will eventually decline into disorder until it becomes the legacy code that everybody hates and dreams to rewrite from scratch, But this time, promising to the managers that, hey, this time we're definitely going to do it the right way. And we all know how such endeavors end. So to prevent such degradation from time to time, we have to shake up the system. We have to identify its weak spots and reinforce them over time. The later we do it, the more expensive this is going to be. So how do we detect those architectural debts? And for that, let's talk about testing. So traditionally, we've got two types of tests. Functional testing for verifying the software's behavior, and non-functional testing for verifying the system's properties. For example, its ability to scale, security, or its usability. I think we should employ a third type of testing, architectural tests, for verifying the system's local and global complexities. In other words, testing how well do the system's modules fit its business requirements. We saw that when the boundaries are optimal, it's easy to find the way around the project. It's evident what the software is supposed to do and how it works. Also, the system is easy to maintain, to evolve, and it is flexible enough to support new business needs. On the other hand, when the boundaries are incorrect, we get the opposite. A system that is hard to change and hard to comprehend. We even have a pattern for such system design. It's called the big ball of mud. According to Wikipedia, it is a sloppy duct tape and spaghetti code jungle. These systems show unmistakable signs of unregulated growth. Information is shared among distant elements of the system, often to the point where nearly all the important information becomes global or duplicated. And this definition almost screams about how. Now, it's easy to understand whether a system is in that state, in the state of a big ball of mud. You know, if you look at the code and you feel that your eyes start bleeding, that's a big ball of mud. But unfortunately, that heuristic is useless. When that happens, it's already too late. We need to identify architectural shortcomings at earlier stages because, again, the sooner we diagnose the problem, the easier it's going to be to fix it and to stop the formation of the big ball of mud. The good thing is, when a system has an architectural issue, we can learn about it from a variety of sources. We just have to be conscious about it. For example, from the developer's point of view, let's say that you have to implement a new feature, but it's unclear to which module this feature belongs. Or when each new feature you implement always affects multiple. Also, let's say you have to change an existing functionality, but the change either affects multiple modules explicitly or implicitly affects other seemingly unrelated parts of the system. In all these examples, we had cases of high global complexity. In other words, the modules are tightly coupled to each other, and the change in one component affects too many other modules. Another evidence of high global complexity is the difficulty to unit test the system. Units are literally spread among multiple modules, and unit tests turn out to be spider webs of those awkward and useless fake objects. That's why I really love this quote by Michael Feathers. He says, unit tests are tests of modularity. And you know, I encountered some teams who said, hey, unit tests are not effective. Unit tests are just about wasting your time on fakes and stops, and when you make one change in the system, suddenly all of our tests failing, and then we're spending another week fixing them. And usually what that leads to is the same team abandons using unit tests in favor of end-to-end tests. Again, what that means is bad module boundaries, fragile design, and eventually high global complexity of the system. QA engineers can spot high global complexity, for example, when some existing functionality changes, but the change in the implementation didn't affect the whole system. That means that the business logic is duplicated across multiple modules. In most cases, when such bugs are observed, the developers didn't even expect the logic to be duplicated. That's an implicit coupling of the components of a system. On the other hand, when QA engineers have to execute too many regression tests, that is also a sign of a high local complexity. It usually means that, when something changes, no one is confident about what parts of the system are going to be affected by that change, and therefore the whole system has to be retested. So when local complexity is high, the system architecture can be improved by dividing the complex module into multiple smaller and simpler modules. Database administrators can also identify a forming big ball of mud. For example, if the system's data is duplicated in multiple databases, but it's impossible to identify which one of them is the source of truth. In other words, when the data goes out of sync, and it's really hard to identify which store holds the correct data. Again, that probably means that the business logic is duplicated between different modules. What that means is high global complexity. Another example would be, when a single user operation affects data in multiple databases, but it's physically impossible to guarantee strong consistency of those changes. And what I mean by that is that business logic requires strong consistency, but the system's design can only support eventual consistency. That's also a sign of high global complexity. And finally, even operations people can be affected by bad module boundaries. First of all, today, lack of DevOps culture is by itself a strong signal that something is probably wrong with the system's architecture. But also, if the deployment process is too complex and risky, in many cases, that also indicates that the global complexity of the system or the local complexity of some of its components are way too high. So as you can see, everybody suffers from bad modules, from bad boundaries. And the person in the software architect's role cannot be in charge of it solely, because they don't necessarily experience all of these issues. They don't have to eat their dog food. Hence, to keep a system architecture in shape, we need continuous feedback from all the people working on the system. Every stakeholder involved in a project has to participate and raise issues they're encountering. And this brings us to good news, bad news. Bad news, this critical approach requires lots and lots of discipline. And discipline can be challenging for some people, me included. Good news, some aspects of architectural testing can be automated. For that, we can use static code analysis tools. These tools process the source code and allow us to do some smart queries to analyze the system design's health. There are many different static code analysis tools on the market, but for demonstrations here, I'm going to use nDepend, as that's the tool that I have experience with. But again, everything I'm going to show you is as relevant for all other tools. So nDepend reads your source code, analyzes lots of health metrics, for example, cyclomatic complexity, coupling, coherence, and many others, and allows you to work with these metrics. The biggest disadvantage of using such tool, maybe disadvantage is not the right word, maybe biggest problem in using such tool that it can be as scary as hell to execute it for the first time. You feed in your source code and then you're getting lots of graphs, failed health checks, everything is screaming red, and you just want to close it, uninstall, and never see it again. So, of course, to effectively use this tool, you have to read the documentation. For example, Independ, it includes over 100 of predefined rules and health checks, and you have to understand what each means and which are more relevant for your project and which one you can just disable. Moreover, you're not limited with the predefined rules. You can also use a query language to analyze things that are important for you. And of course, you can generate different graphs that visually describe the state of the system's design. For example, here we can see a pretty high global complexity. Looks like all these namespaces are tightly coupled to each other. There are many different references and dependencies between them. On the other hand, let's say that this one is a diagram of a single module. Here we can see a typical example of probably high local complexity. Why am I saying that this is probably high local complexity? Well, because we have this part here. And that's an interesting part because we can see that it has many components, but it kind of loosely coupled to the rest of the system. There are no many references between these parts and the rest of the module, which means we can divide this module. And by that, first of all, we're going to reduce the local complexity of the original module. The one we're going to produce is going to have low local complexity because it is definitely going to be lower than the original one. And we're also not going to raise the global complexity of the system because, again, it's pretty much encapsulated and it's not going to introduce many. Now, the weak side of static code analysis is estimation of global complexity between microservices, or for that matter, of components of a distributed system in general. And it's challenging because usually microservices are implemented independently and often in different languages and platforms. So what is we can watch over the changes in the module's public interfaces. For example, amounts of public methods or message types emitted or subscribed by a service. Now, it's important to stress that these numbers are not absolute. For example, you cannot say that more than 10 public methods is bad and less than 10 is good. No, there is no such magic number. Instead, we are interested in observing the trends, how modules' interfaces are changing over time. If they keep growing bigger and bigger, it might be a signal of growing global complexity of the system, and as a result of a growing big ball of mud. And to observe such changes, we can integrate static code analysis in CI pipelines. Then for each build, Independ will calculate the metrics and build reports about the changes over time that we can observe and that funny things are happening to your services. Now I want to talk a bit about what causes a software to change. The evolution drivers. So the first one and the most in my opinion, it's one of the most implicit reasons for change is changes in the organization that develops the software. So if I'm talking about Internovus, for example, we started as a small company. We were just two people in a garage. But over time, in about 5 years, we became a group of 3 medium-sized companies. And all of them were located in different countries. Integration mechanisms that worked for us in the startup days, those ad hoc collaborations, like, I'm telling someone, hey, I'm changing the public interface here. And the second person says, hey, sure, no problem. I'm just going to change my module as well. No drama. This no longer work for large organizations. When your organization becomes bigger, you need to introduce different, more formal integration mechanisms. You suddenly need to version your APIs, and probably you also need to deploy multiple versions of the API simultaneously, so that all dependent teams can migrate their projects in their free time and not at the same moment, like when everybody have to coordinate their work. Coordination doesn't work well over long distances. So that's something that we have to keep in mind. We have to keep an eye on that, because changes in the organization often lead to changes in the system design. What was perceived as a low global complexity in a startup company can suddenly become an insanely high global complexity in a larger organization. Next, let's talk about the business-related change drivers. So in domain-driven design, we differentiate 3 types of business components, business subdomains, business responsibilities, if you will. And not all of these business subdomains are equally important. So first of all, we have components which are implementing the company's competitive advantage over its competitors. This is the company's core business, the core subdomain. These are the areas which are crucial for the company's success in its business domain. And these are the areas that are going to change the most. On the other hand, we have supporting subdomains. Well, these are components which are there to support the business, the core business, but they are not mission critical. That's not how the company is making money. For example, at Internovus, we had one of our core businesses was managing advertising campaigns. And to do that, we have to manage our creative catalog. Well, managing banners and landing pages and putting a search index over them, that wasn't our core business. That wasn't how we were going to make money. So that was our supporting subdomain. And finally, the third type of subdomains is what's called generic subdomains. And here we're talking about the same solutions which are used by all the companies in the industry, both by the company you are working in and its competitors. These are the solved problems. For example, trivial example is data encryption. Well, you just want to use a proved solution. You don't want to invent your own algorithm. Same goes for accounting systems. Now, the first thing we have to keep in mind is that these 3 types of business domains, they're changing in different rates. The core business is going to change the most often. Supporting subdomains, on the other hand, are going to change the least often, because business is not interested in optimizing them. And finally, generic subdomains are somewhere in the middle, maybe going lower, closer to supporting subdomains, but sometimes the solution still has to change. For example, security patches and stuff like that. So first of all, we have to keep in mind the different volatility rates of these components. Second, Especially in startups, the business strategy often changes, like it happened at Khononov. We changed our business strategy multiple times, and we even changed our whole business domain once. Now, when that happens, types of subdomain can change. So what was a supporting subdomain yesterday can suddenly become a core business, and suddenly it's going to change much more often than it used to be previously. So that's also something you have to keep in mind, keep your eye on when designing software. Software, the design which fitted the previous business strategy won't necessarily be a good fit for the new business reality. And I think I'm going closer and closer to the end of my time slot, and that's the time to wrap things up. So, software architecture manages complexity. We saw two different types of complexity, local and global complexity. We have to balance both. Neither is more important. Everyone suffers if module boundaries are ineffective, and you have to look for symptoms of bad boundaries. These symptoms are everywhere. You just need to be conscious about that. And of course, react immediately as you encounter such issues. You can use static code analysis tools to control code base evolution, and keep an eye on changes in the organization structure and business strategies that affect the design of your software. A book I can recommend about this approach of building evolutionary architecture is, of course, this one, the classic one by Neil Ford, Rebecca Parsons, and Patrick Qua, Building Evolutionary Architectures. And I still have a few minutes for a shameless plug, so I also recommend these books. So about a year ago, I written this book, What is Domain-Driven Design? It's a guide to domain-driven design that you can read over a flight, something you can finish in an hour, and you will gain enough information about this methodology and how you can use it in your day-to-day work. It's about 90 pages long, really short book. It's available on O'Reilly's online learning platform. That's the link. If you're registered, you can just read it. If not, they're giving you a 2 weeks free trial. So 2 weeks is more than enough to read 90 pages. Also, I shared the story of Khononov using domain-driven design for 7 years in this book, Domain-Driven Design, the First 15 Years. This one is available for free. If I still didn't bore you to death, please give me another chance. That's my Twitter. Also, I'm working on some other projects which are going to be related to the topic of this presentation, but I cannot talk about it right now. If you want to be first to know about it, that's my Twitter. And with that, thank you so much